And turn on the live transcript. And let's see. Chat back up because I missed. I won't know how well everyone did on the test. The high score I noticed was 81%. While that wasn't all the submissions at that point in time that I saw that. But I won't know until tomorrow what the metadata looks like. Let's see, the recording start. Yeah, okay. All right. Yeah, so the lowest test is dropped. It's probably showing this current test being dropped for you already, because as far as Canvas is concerned, it's graded, even though it's not entirely graded. So it's already going to be reflecting that. I think it grades it out from your perspective. But I still have 16% of the score to tally up. No, tests are not curved.
Figure it out based on today's dollars.
Okay, tree questions. Differences between roots and leaves. 2 area trees, 3 area trees. There hasn't been an EC, extra current opportunity? No. I primarily do that via the dropped test. Sometimes on tests, there will be extra credit points on the test when there's an area where it's just not a good area to have on a test because there's ambiguity or time or complexity. Usually I toss those as the extra credit bucket to see if you are handling the more complicated items. We're still in the trees section, so let's check. All right, we're still in 11 and 12. Or no, 10 and 11. Numbers straight. No, there's no. Should pretty much be everything. If there's, I can get you some more web resources to check out if you've already run out of book stuff and our trees sections here in the modules. Top of that seems to be missing a link or two. That's nice broken. Let's see. Our general trees, double check and make sure I haven't forgotten anything. All right, we've talked about all this good stuff. Tree height. All right, tree order trees, binary heap. So any questions about heaps or AVL trees at the moment? I think we'll want to re-hit those tonight. Yeah, those links back to sequence. Okay. Let's see where we were. All right, so our AVL tree, part 2. All right, so we're just going to build some more trees. watch them grow.
But if we're not doing any frills and it's just like,
And it'll be slightly abstract here without any data.
but if you're planning on having like any kind of discretionary spending, like travel.
All right, so
or-
remember, it is a binary search tree. So we will build as the data grows. So whatever the data points happen to be, the tree is growing in this pattern. All right, so when we look at the heights here, backwards. Back, go. Right, so the root of our tree, looking at the heights of its subtree, where we have a null subtree on the left-hand side, right? So let's draw this subtree here, but this tree subtree is null. It does not actually exist. So this pointer, the left pointer, is also null. Our right pointer from our root node has this tree over here. It's a subtree, also an AVL tree, so it's following all the rules. Binary search tree. It is ordered from left to right with our lower values to the left and our greater values to the right. And this tree is reporting a number of levels, right? So if you don't like the -1 height aspect, you can just look at the level count, right? So the number of levels in this left subtree, the empty subtree, has 0 levels because it's empty. Right subtree, it has 2 levels. Right, so the difference in the number of levels between these two subtrees is greater than 1. When we have that situation, we're going to require our rotations. Right? This leaf was our newest node. It was inserted into the right subtree. The right node is reporting the heights being out of balance. Right? So remember, AVL is a height balanced mechanic. Since we went right, 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 single rotation of this node, which we're calling beta. All right, so call this AB for short. Rotate B to A. And the tree gets back into a balanced state. B and its subtrees move up. And we're back into a balanced state. Now, if we go ahead and look at the heights of our subtrees, get there, back. Right, we see that they have the same number of levels or the same height. In whichever way you want to look at it, it's effectively going to give you the same style of metrics. So the tree is good to go. All right, so this is right addition. We'll have the mirror case as well, but let's go ahead and get some data points in here now. Now if we come along and add
Do we want to add
4.
about 10K and factoring inflation growth?
4 is
as well?
going to go to the left, being less than 9.
Because that should be simple enough.
Of course, 2-node tree is going to be as balanced as we can make it, so there's nothing else to do at this point. But if 7 comes along, go left from the root, right from 4, And then 7 gets added in here. This time we inserted in the right subtree, the left node of the root of a subtree, or the entire tree as it is in this case. It's reporting imbalance. 2 levels. Left-hand side, 0 levels, right-hand side. All right, so that means we're going to have 3 named nodes in this case. Let's see, alpha's A. What color starts with A's? Yeah, I guess beta can be blue, gamma can be green. Somewhat of a color sense there. I see there's a question. Why was B the root? B was the root because B was beta. Took the beta node up, rotates it up the tree. Its parent slides down. That pushes, so it pulls weight from the right side and then shifts it over to the left side. All right, so this time, to the right subtree of the left child.
It was after.
So we're going to have a double rotation. Rotation. All right, so 4 is beta, 9 is alpha, and 7 is gamma. So beta, gamma towards beta, then gamma towards alpha. Those are 2 rotations. All right, so our blue node beta is going to rotate down. This gives us still a binary search tree. All right, so in this temporary state, we'll take a look at it. 9 less than 9, 7, less than 7, 4. Still a binary search tree. As we do the rotations, it's always going to stay a binary search tree. Now, if we were to look at this, right? So if we had just 9, 7 to start, and we added 4. Look at this binary search tree. We see we have 2 levels on the left-hand side and 0 levels on the right-hand side. So we'd have an out of balance situation. And we did an insert into the left subtree, and the left child, right? So we have left, which is just single rotation. All right, so our first rotation brought us into our simpler case. Now we can rotate again. 7 goes up, 9 goes down, and our tree is getting back into a nice, ideal triangular state.
Well, I think this is also going over like who does the investing and if there's any trust and stuff involved.
As the tree gets bigger,
so we could probably just keep it.
It's the same story. It's just there's more branches
We're doing it.
to keep track of.
So I think when he was going over it in the video, it was like talking about
So we just
like
need
if you're directing someone to do the investing for you,
rotate as needed.
or like if there's a trust involved.
So as the tree's balanced to start, it's going to take quite a few more data points.
Like attorneys and stuff involved.
Start getting out of balance.
But we could probably just keep it simple.
Binary search tree
Be responsible for it ourselves.
grows as a binary search tree. The fact that this is an EVL does not change the growth mechanic. Just grows as we need to grow, starting at the root. All right, so if we come in at 2, lower than 7, lower than 4, ends up in the left subtree. But now, if we look, Seven's left subtree has 2 levels in it. 7's right subtree has 1 level in it. if the left subtree gets an additional level, then the 7 node is going to fall out of balance and require rotation. So depending on which way we branch at this level, right subtree or the left subtree, that's going to drive how to do our rotations. So let's go ahead and do both scenarios. All right, so go down both ways. Right, so we can add into this subtree by adding a 3, or we could add into subtree over here by adding a 6. All right, so going to the 3 first, we work our way back up the tree to make sure that the subtrees are happy. All right, so our 2, 3 subtree is happy with their heights. Work our way up to the 4. 4 has 2 levels on the left, 1 level on the right, so it's happy. And then we work our way back up to the root, where we see 3 levels on the left and 1 level on the right. So we're going to cause alpha node. All right, and then we'll have the same situation here if we were to add 6 instead. 5, 6 trees happy. 4, 5, 6 trees happy. Right, just a mirror situation at that level, but then 7 says 3 levels on the left, 1 on the right. That's too great of a difference. So we're going to have to do an update. There, add some text. Same point. Value which will drive what data rotations need to be done. Okay, so with our 3 insert, we went, it's a little bit too dark. Okay, into the left subtree of beta. So we have a left pattern, single rotation should bring us back into balance. Work my white space here, get everyone to fit nicely. All right, so beta wants to work its way towards alpha.
Yeah, so I think,
In this process,
I think
let's
also
explode this.
his thing is desired is high, but his requirement
Leave
is
it
output.
steps,
So
one step at a
trying
time.
to make those two make sense.
All right, so beta rotated towards alpha. And create some of this white space along here. Again. As you see this rotation, we have our tree into 2 pieces at the moment. We want to make sure that these are all staying together. When we rotated, right, 7 had 4 as its left child, which is our beta node. Add some text here, make sure some context. Where's beta? Or beat. laying down the beat. All right, 7 is alpha. 7 previously had 4 as its left child, right? So we know we have a vacancy there. 4 wants 7 to become its right child. Right, so we'll need to shuffle our links around. Depending on how you code it, the order could go either way for who we link first or second, but go ahead and link beta to alpha to start. Then we'll take a look at our binary search tree at this moment. And we have 4 as the root of this tree. Left subtree value is less than 4. Right subtree value is greater than 4. And we have the 5 node that wants to get reattached. Right, so 4 and 7 were its ancestors. They will continue to be their ancestors. And the tree is as triangular as we can get it. And it's good to go. Now carrying forward. The other situation. When we inserted slightly different place. Right, so we have the same node complaining about the heights. This time on the path of insertion, we changed directions. Right subtree is the left child of our alpha node. So we're going to have to do a double rotation. Alpha, 4 is beta, again like before, but this time we need to add gamma in here, just like before. Gamma goes towards beta, then gamma goes towards alpha. So when we rotate beta towards gamma, or the other way around, gamma towards beta, it's going to cause beta to slide down the tree. And gamma to go up the tree. All right, so we're trying to straighten out this insert to make it a left-left scenario. We did a few minutes ago. Taking over its spot. In the previous location, right? So if we compare the previous state, 7 at the root, 9 to the right, 7 at the root, 9 to the right. Just do a little rearranging here. So 4 and 2 work their way down. 5 and 6 work their way up. Right, 5 and 6 was the tree that was too tall. Part of the tree that was too tall is getting itself shorter, but we can't just stop here, right? It's still a binary search tree. A root is 7, values greater than 7 are to the right, and all values that are less than 7 are to the left. But there are 3 levels on the left-hand side of 7 and 1 level on the right-hand side. So we can't stop when you keep going. This gamma needs to rotate towards alpha again. So we'll continue with our rotation. 7-9 part of the tree rotates down. 5 will take over. 7 as its right child. And then 6, like before, 5 and 7 were its ancestors and remain the same. And binary search tree still. 6, 7, and 9, all greater than 5. 2 and 4, less than 5. So as nodes rotate their subtrees, want to get pushed and pulled along with, but then a little bit of switching around in the parent tree. Questions about the AVL tree at the moment? Let's swing back to the B tree again. AVL and the B tree tend to be areas where more points are lost on the test than others. 1, 2. Do it again. There's 0.9. More B trees. Transfer 233. Building. All right. First few states. Not a whole lot going on. Remember, we're looking for a leaf. Once we find a leaf, go ahead and insert our data into its sorted position. So if 15 is our first data point, create our node, that's the root, and we add it in. If 10 comes along, go ahead and insert that into the root as well because it's a leaf, and it does push 15 over to the right. So remember, we have left to right data pattern with our B trees, just like we have with our binary search trees. So the data is ordered left to right within the node, and that controls the relationship of the subtrees as well. All right, so let's do 3 alternatives. We go ahead and add 5. From this point, adding 5 wants to put 5 to the left of 10. There's no room for it. The middle value gets promoted. So we'll have 10 going up the tree. We'll have 5 inserted into our existing node, and 15 into a new node. All right, so we went from a single node holding 2 data points, and we're growing to 3 nodes. Okay, there's no other way we can arrange our 2-3 tree differently. One node can only hold 2 data points because that's what's in the data structure. Besides the array, we can hold 2 data points. So we don't want to overflow our array.
Annually.
I can't have 15 as the root with 5 and 10 stuffed down on the left-hand side, because if there's one data point in an internal node, it's telling me that there are 2 branches. So I can't try to shove this into a 2-node formation. It's impossible to have 2 nodes in a 2-3 tree. It's just not going to happen. Right? Once we grow, we'll have at least 2 nodes in the second level and 1 node in our root level, first level. So go ahead and link these together. First pointer goes to our first subtree, values less than 10. Second pointer goes to our second subtree, values greater than 10. We'll have a similar pattern if we add different values instead of 5. Right, if we added 12, we're going to end up with 3 nodes again. But instead of 10 being promoted, 10 will stay where it was. 12 is the median value. 12 gets promoted up with 15 going over to the right. In the same thing, instead we added, say, 27. 10 is the smallest value. It stays where it is. 15 is the median value, so it gets promoted. And 27 is one that gets created into the new leaf node. All right, so 3 different additions. How we're doing with this for the moment. Somewhat making sense. All right. Let's keep growing our data. There's our initial point. If 40 comes along, 40 is greater than 15. So we go ahead and go down second branch, find the leaf, and there's space for it, so we just drop the data point in. We come along, want to add $60. Just like with 40, start the root, greater than 15, find the leaf, we want to add to this leaf. This leaf does not have space. All right, so we're going to have to create a new leaf. We'll hold on to 60. And 40 is working its way up the tree. All right, so 40 wants to go up. Forty goes back up the branch that we followed to get here. And since there is room for it, you can go ahead and drop that value into the root. Now that the root has 2 data points, we now have 3 children from that point. So go ahead and move things over a little bit. 2 data points indicates 3 children, whereas before we had 1 data indicating 2 children for non-leaf nodes. This is a 3-4 tree. We can do a 3-5 tree. 3-5 would be the next level up. So after we get this one built up to 3 levels, I can show you a 3-5 tree. All right, so let's leave this drawing where it is. Get another one going. State. And we can go ahead and add any data point we add now. We'll just find a swing to a leaf. So we'll add here. All right, so what are the range of values that we could add to this tree at this point in time, such that it ends up in the 27 leaf? What's our smallest value that we could add? 28 would get in there. Can I get something smaller? Remember, when we're inserting, it's like a binary search tree. We start at the root. So what data points, right? 16, the smallest value greater than 15. And then if we look at our upper bound, 39 would be our upper bound for values that would end up into this subtree. So if, like you said, 28 would be the smallest value that ends up in this node. 28 to 39 for values that could end up in this node. And then 16 to 26 would cause 27 to slide over. And so if we go ahead and add 18, that pushes 27 over. And no structural change for that addition. Now if we add any value in that range, say 20, we'll overflow our 18 leaf, and we'll have to go ahead and cause some splitting to go on here. All right, so make some space. I want to add 20. 20 will be median value. So 20 is working its way back up the tree. 20 is hitting our root. The root is already full. It's going to have to split as well. All right, so we'll have 15, 20, and 40 in the root node. 40 pushes over. And 20 is going to be promoting its way up. We got 20 here, floating its way up the tree. Right, so when we tried to add 20, right, let's put it here. 20 is trying to get in here, in between 18 and 27. So the median value, once we get it to the leaf, is the one that pushes up, right? Because it's the one that splits. It's a good, it works as a good parent for 18 and 27. So there's our 20 working its way up. All right, so before we keep carrying 20 along, let's do some housekeeping on our pointers here. Right, so 40 wants to bring some links over along with it. And our newly created node, we want to go ahead and link to that. Let's see if I can get these. Right, so if we were just look at this little part of our B tree, this is A23 tree. We have 40 in its root, 27 first subtree, and 60 second subtree. Right, so now we have 20 working its way up. Since there is no node above 20, we are creating a new root. 20 fits into the new root. 20 is going to point to the existing root or the previous root. And the new node that's split off of the old root. All right, so here we had 15. 15 was our old root. 10 and 18 subtrees or subnodes stayed where they were. So if we look at this subtree, that's still a 2-3 tree. 15 has subtree with values less than 15 first branch, greater than 15 in its second branch. And then we have 20 in the new root, and then the subtree that contains the values less than 20. Ooh. Things falling down in our backyard over here. And values greater than 20 in the right subtree.
Mommy, what is that? Mommy, what is that?
How did I know?
I think on the instructions, it's just
Oh, let me see. The question was, how did I know not to add 20 to the root node? So we never, remember when we're adding data, we start at the root and navigate down to a leaf. Once we identify the leaf, we fill data into the leaf. The leaf does not have space. The leaf node splits. The median value promotes, and that promotion can lead to a chain reaction of splits. Well, 20 went to the middle branch because it's greater than 15 and less than 40. Right, so it's similar to a binary search tree. We're looking at left, right, pattern. Ooh, here comes the sun. All right. All right, so whenever we add a new data point, so we're adding 20. Right, so we start the root. So let's rewind and redo this one. Adding 20. 20 is not less than 15. So we go ahead and look at the next data point. 20 is less than 40. So we go down the second branch. If we were to add 70 instead of 20, not less than 15, not less than 40, so we go down the third branch. Yeah, so, right. Yeah, so remember each node, whether it's a leaf or an internal node, only supports 2 data points. And it's like a binary search tree. Binary search tree, we go left or we go right. But now with the B trees, we iterate down the list and then select the appropriate branch to grow down.
I don't know.
So if we wanted to do a 3-5 tree, 3-5 tree, which is a bigger size B tree, and test grab these nodes. Actually more relevant because 2-3, the reason we're doing a 2-3 tree is because it is just the simplest. Structure that is a B tree. And so here's our node. We have 1, 2, 3, 4, 5 links. So we have made 5 children, 4 data points. So we'll just add 20. 90 come along. All right, we're still a leaf. And let's shrink this a little bit. Go ahead and add 70 in. 70 pushes 90 over. And if we add 15, all right, 15 pushes everybody over. We draw it like that. And we finally have a full, it's a 3-5 tree. Usually, it's about a 2-to-1 ratio of the min to max. Number of nodes, child nodes a node would have. All right, so let's add 50 because it's a nice split. And we want to try to add 50. Right, so same idea. Median value promotes. And then we'll split the data. Half the data. Well, let's see, it's gonna be a 3-5 tree. Or the 3-5-2-5. Trying to think what my next smallest B tree could be. Can be 3-5 or 2-5. Oh, I said it's a 3-5, so let's. I've never even done a 3-5. I'm gonna have to think here. It might be a 2-5. All right, let's say it's a 2-5. Let me rephrase. Maybe this is a 2-5. One step at a time here. Okay. So we're going to keep 2 of the data points to the left and 2 data points to the right. And we have a new root with 50 in it. And this is the idea here. Subtree less than 50 on one side, and subtree greater than 50 on the other side. And the key difference here is how big our nodes are going to get before we start to our splitting. All right, so remember for our B trees, the 2 numbers, the first number is your minimum number of children, and the second number is your maximum number of children. And the number of data points that you would find in your internal nodes would fall along those numbers. So we have a similar pattern here. As nodes fill up, we can start breaking them apart, split the nodes, and promote. As we actually get to fuller scale B trees, actual implementations want to avoid splitting and collapsing the tree structure as often as it can. So what things could happen if we start filling this up? Right, add some more data. We had 30 and we had 35. And let's move this to another drawing. It's coming down pretty good over here. Apologize for any rain background. All right, so if we want to add, right, we could split, all right, it's less than 50. So we could split this node and promote 30 up the tree. Then we have 30, 50. All right, let's do both ways. All right, we're gonna add 40. 40 once right there. We'll go ahead and do our split. Split it. $30 and $35. Come over here. Pulled from node over there. 40 moves up. Right, so the pointer down, just like we have the 2-3 tree. 150 slides with, comes in, and we have 2 data points. We have 3 children, subtree less than 40, subtree between 40 and 50, and subtree greater than 50. All right, so the other thing that we could have done is a little bit of thing. There, so we shift instead of a split. Rightmost value of the node up, and parent shifts over into the child. If this works, if the adjacent leaf has space. All right. So we make room. 40 wants to be the rightmost value, so it moves up. And then 50 can push. It's not working the way I want it to work. Over here. All right, so it keeps the node structure. That way, eventually we'll run out of space, so we'll just delay the splitting, but sometimes they'll do this to avoid pushing values back up the tree. Again, we're keeping our scenario with 2-3 trees, keeping things as simple as we can for now. All right. Okay, let's go ahead and take a 5-minute break. And we'll come back. Going on mute. Okay. I've gone through the grading for program 1 on to. I'm gonna do two things. I'm going to go over structure. So structure level. I'm just going to use C# because faster and less code. Give you an idea of kind of things I was looking for. Program 1. There's always more than one way to slice this up. Under language, next. Always fun switching back to the language. Okay, so the stack part of the assignment wasn't very exciting. We already had labs to affect that good stuff. As we have our push and pop. Take whatever data you're doing, bring it to your stack. Syntax between C and C++, Java, C#, all very similar. And then all the newer languages have gotten rid of stars for the pointers and just gone more of a reference-based pattern. You may remember Michael Atkins. We were talking about trying to reduce unnecessary code, right? So our push function, if you're doing things this, it's perfectly fine to keep your logical branches set. But as you start looking at your code, and look for patterns, look for things that where you're doing logic in multiple branches. Actually start to have 4 or 5 branches and see in here, but then you see the same being repeated over and over again. All right, we can apply this. The stack is empty. Stack is empty when the top is null. So we're going to go ahead and say the top is in, and top next is null. Let's do close it here, say here, our next. Otherwise, and next equals top, and then the top is n. Right, so if this were true, if the top were null, and we went ahead and did this, and next equals top, the top's null. So we're just redoing what we previously did. We're saying n next equals null. So this line of code doesn't really even care if the top were null or not null. So we can go ahead and simplify all this good fun stuff and get rid of that, right? So we saw C++, same idea, different language. Carry on. And pop. At the moment, I don't have accounts to make use of. So we'll just have to make exceptions. Stack is empty for the moment. Very trying to offer an empty stack. Doesn't work so well. One of the advantages of C# and one of them is that we don't have to worry about memory leaks. So we're talking a little bit more. We're talking about program 1, our reverse push stack. And more specifically, at the moment, memory leaks. In C++, again, a lot of code submissions, there's been plenty of memory leaks. In a memory managed language like C# or Java, other languages, I don't actually have to do the delete. Don't have to worry about memory leaks. Anyways, here we have our link-based stack. And moving on to our calculator. Since all we want to hold on our stack is operands, I'm just going to label it. And just go ahead and calculate based on expression, all this good stuff. And we don't need that memory, which is going to be local sort stack of operands. Stack. Carry on. All right, so just go ahead and split up our data and work through our data points. So whatever way you want to break apart your data, string stream is what I was trying to push you on with that early on our first week lab. This is C#. Right. However you want to break apart your string is not particularly pertinent to the stack data structure or the calculator itself. So string stream, go on and just, some people, I think, one or two people use Sturto because some people are still feeling stronger in C than they are in C++. It's perfectly fine, right? If it's got a .cpp file extension and it compiles, we'll go ahead and count that as C++, even though you're not using class, right? And really, how many language features of C++ do you have to be used for it to be C++? Do you have to use inheritance, polymorphism, generics, or ref templates, all that fun stuff? Doesn't much matter. Right? Different languages have different ways of dealing with getting data. So we had two things to do. If it was a number, what are you complaining about here? Let's see a second. Nothing at all. It's always fun when the background compiler is behind things, right? So if it was a number, we just push it. Operands. Push a number, and we're good to go. Otherwise, calculator logic. Right, if we try to pop from our stack, we want to get two values. We want to pop from our stack, get our left-hand side, and get our right-hand side, and then operate on them. We'll do our error handling here in a second. Right, so here's one of our various things here. If we're adding, we just push the result. Left-hand side, let me get these backwards. Hands backwards. Right-hand side first, left-hand side second. Push left-hand side plus right-hand side. And we're down switch. We're not pulling out. Minus, multiply, divide. Right, pretty much same code, copy, paste, change the operator. Multiply, divide. Should want some intensity because the 0 tends to be bad. And so we'll do our first error case. Yeah, we'll keep it simple. Let's there. In code, we should start testing this. Closing curly braces here at the end. At the end of this, pull from our stack and everything's good to go. Then we're good to go. So let's go ahead and create my calculator and do some hard-coded testing to start off with. As usual, pretty much every language likes to have its own way to slice and dice right to the console. That's one of the things when I'm teaching C, C++, or I'll point you in the direction of ways of formatting your I/O out there, but it tends not to be worth a whole lot of time doing all that, doing too much work because studying on that because it's going to change to see which language is. Let's see, so expression n equals, let's see if our calculator is going to work. What I call my function, calc. I didn't type that right, which is why I didn't. This. And our expression. So let's see what I broke. Plenty of red squigglies here, plenty of opportunities to fail. But sometimes you get lucky. All right, 5 plus 4 is 9. And we're not handling our cases very well. And if we go ahead and change our expression. Wow, typing. Such an overrated skill. Right, 4 plus. It's gonna fall down. Nice explosion at runtime. If I get my semicolon in there, that is. All right, we got our stack error. So dealing with errors. 2 ways we could have approached this with our calculator. There were several ways we could approach this. When we know we need numbers, we know we need there to be at least 2 values on our stack. So one way we can approach this is to do, right, common thing we have here is empty. Public school is empty. Right, we just return back. Yes, the top's null. Yeah, if the top's null, it's gonna say it's empty. So one way we could do this, we just test the stack. If it's empty, we know we've got a problem. All right, we can go ahead and spit out an error message. Right, in our case, we had what excessive operators, whatever the error message is. We can't do our job. The expression is not what we want it to be. So I'm just going to bail out of this. One. And then copy paste, do it again. Right, we pull the number out, then we check to see if our stack's empty, and then the same code again. Right. Probably 97 to 99.9% of the time, you're copying and pasting code. There's a better way to do it, because having the same code exists in more than one place. Bad pattern. If I'm copying this code and then changing the code, well, it's not the same code anymore. Sometimes that means you could have created a function, you just move that code that you were going to copy into a function and then just parameterize things. That way you don't have duplicate code or near duplicate code floating around. So this solves our problem, right? -1, too many operators, bad output, whatever. Right, right. Don't repeat yourself. It's a very, very good habit to get into. Doing code reviews, and I see people copy paste code. Whew, that's automatic code rejection. That's one of the things that irks me, because it's a pattern that we all tend to fall into a little bit too often. Right. So if we keep track of the count, our calculator can get more intelligent. Because our calculator knows that it needs 2 values. To do its job. So if we expose count, and anyways, so if we make the count part of the stack, whenever we add, we increment, and whenever we remove, we decrement. Now, instead of having to check it's empty, we can just let it count. Right, so if count fewer than 2, we have the problem. We have too many operators, and I don't have to make this other check again. We just go ahead and carry on, right? So if we have 2 or more values, operands on the stack, we'll get past this check, and we'll be good to go. Carry on, right? Test my code, right? Same output. Too many operators. I can't evaluate 4+ because it's not a valid RPM expression. Right now, there's less redundant code here by adding this count capability to our stat class. Same thing here. At this point, we expect the count to be equal 1, and if it's not, then there were too many operands. Excessive.
All right, we don't have that test case in here just yet, so let's add it. All right, 4, 5, 6. All right, that's got too many operands. More data, and we have operators to work on. And then lastly, we have divide by 0 yet to be accounted for. 4, 5, 0 plus divide. Which way is my divide operator? Did I go that way? Yes, that's good to go. 4, 5, 0 plus. And too many operators. I got a bug in my code here. Seems I have a bug somewhere. What's going on? My mic got a lot better. I guess my internet improved. It sounds like the storm died down. So I think the static you may have been hearing from the rain battering on the roof, which I could hear, it was coming down quite heavily. Interesting. Yeah, my code is working more than it should be working, so I have a little bit of bug here, but otherwise, they're divided by 0. Right, if just is equal to 0. We've got our bug here. Divide by 0. Bad. Blue screen of death. Depending on the language you're running. So we don't want to do that. So just go ahead and bail out. At this point and carry on. -1. All right. Bolt line shock the internet, it's possible. We had fire or 2 set from the lightning in our area a few weeks ago. Didn't need the result. Okay. Right, any questions about the calculator? Obviously, the main part needs to be a little bit expanded to meet the requirements for the loop, but I wanted to hard code my test cases, so I'd have to retype them for the demonstration, so I didn't do a while. Otherwise, it's just while the expression is not 0, just pass that expression back into the calculator. Have it spit out the result. Okay, now let's talk some more about pointers versus objects. Because based on a lot of the questions that have been going on over the weekend, what is going on? Okay. For program 2, help clarify the difference between a pointer and a node. node star temp equals new node. All right, so that node's data equals I and I guess I'll just add a node star top example here. Temp equals top and top equals temp. All right, so and let's split this up here. Temp equals new node. All right, so temp is just a pointer variable. All right, so let me just go ahead and do a print loop here. Node star current equals top current. Print out the current data. I think I called it data, right? Yes, data. Some white space and current. Get my arrow there. Current, use current next. All right. So where is my drawing? Annotate and we will draw. So 0. So we create temp. Right, temp is just a pointer. New node comes along and we create the box. And then we say temp points to our box. And we say temp data equals I, right? So our arrow dereferences our temp pointer and then gets us to our data field. So we can say data, right? Data is 0. And then temp next. So again, the arrow dereference our pointer variable temp to get us to our box and specifically to the next part and set it equal to top, which is null. All right, and then top equals temp. So now we're saying top also points to this same box. So we got 2 pointers, both pointing to the same box at this point in time. Loop around, I goes to 1, temp pointer, create a new box, new node. So new node says create a box, empty box, no data, no pointer, or 0 data, 0 pointer, depending on how good the constructor logic is working. Temp data, right? So like temp, you get hit like temp equals new node. All right, so the new node, the new keyword tells you where in memory this box is, and the assignment operator says we can point to it. So now temp no longer points to the old box, points to the new box. So we dereference temp, set the data to 1, set the next to equal the existing top, right? So we go see top, its memory address is this 0 box. We go ahead and point to the 0 box. Yes, top and temp are the same for a point in time. Then we replace temp with a new box. Right, the question was, but top is pointing to temp, not when temp is pointing to. So as with all programs, timing is critical, always critical. Timing is the most critical thing in a program, especially when you got threads floating around. Right, so here we're on our second pass. Temp is probably still the same variable in memory, right? So if I move temp out of the loop, right, probably still the same variable in memory. The fact that it's nest and scope here probably not change anything. So before we get to 26 again for the second time, both temp and top are pointing to our 0 box. But then 26 gets evaluated again. The assignment operator comes along and stomps over the old value of temp, causing it to no longer point to 0 and instead to point to 1. So when we dereference and set data equal to that 1 value, that's what gets the 1 to be over here as opposed to the previous location. And then we said temp next equals top. Top is the 0 box. We have our temp pointer pointing to this box, and it navigates into our next pointer, and that points to our 0 box. Yeah, it's a head pointer. So then 29 evaluates again. Top is no longer pointing to our 0 box, and instead it's pointing to our 1 box. Loop again. New node creates a box. Temp equals new node. So now temp forgets about 1 and now points to this empty box. Go ahead and write 2 into the empty box and set the next pointer equal to the existing top. So top, read top, memory address that is stored in top is where the 1 box is. So we point to our 1 box, right? And then that just continues with 3 and 4 rolling in with top being updated each time to point to the top. So then we go ahead and loop. All right, we set current equals the top. So here's our list. 4 points to 3. That's a great looking box there. 3 points to 2. 2 points to 1. And 1 points to 0. 0 points nowhere. All right, so we create another temporary pointer called current. So this is its own little temporary pointer on the main stack frame. Read the value from top. Top is pointing to 4. So now current is also pointing to 4. That's not null. So our while loop is good. Spit our data, spits out 4. Current equals current next. So we read the next pointer, the current box, which is our 3 box. And we copy that back into current. So now current shifts on over. That's not null. So we go and spit out 3. Reads the next pointer, which is the 2 box. So current now points over to 2. And so on, points to 1, points to 0, and then points to null, which causes our loop to stop looping, and our program finishes. All right, so pointers track where in memory something is. If that something is a node, then we're talking about just whatever fields is that node. Right? If it's like a char star, like a C string, right? You're just tracking where that first letter is. And then all the other boxes of letters are just floating around in memory, right? Starting from that one point that you're pointing at. It's the same thing with structs or objects. You're just pointing at the beginning of the box, and the dot or the arrow just offsets to whichever part of the box that we're referring to, be that part being data or that part being our next pointer. All right, so if we expand this, like for program 2, it's the same thing, except we need more pointers for program 2. And we have 2 beginnings of the lists, our low names, our low weights. And then we have our next name and our next weight to account for there being 2 data points. So you're just replicating the pattern that you would already have for a sorted singly linked list. Yes, that was a stack. So we were doing a stack that was singly linked because there's just one pointer. So then when there's 2 pointers, now it's doubly linked, right? You doubled the links. And what we're doing with program 2 is we're doing doubly sorted. So we'll use one link to track where the next weight is in order so that we get 100, 120, 140, 190, 225. If we start at low 1 and iterate through our next pointers. We start printing at low 2, and we'll work on our next 2 pointers, and we'll just maintain the next 2 pointers for Abe, Carla, David, Eric, Francis, Georgia, whatever the names happen to be. Key thing is, if there's one person in the list, there's one node. And those next pointers would both be null because there's no one after them by name or weight. As new data points come in, it's just 2 logic pathways, one logic pathway to get weights in order and one logic pathway to get names in order. Right, so I've graded most of the programs I've did before today. If you lost points, it's usually because you make one list. So the common mistake is you have 2 lists, either because you explicitly said list 1, which has 2 pointers and I'm only using one of them, and list 2, which has 2 pointers and I'm only using one of them. The other thing is adding. If you create 2 nodes, when you're adding to the list, you're creating 2 lists, right? If you were to actually, if you change your print function to print out the values of your pointers as it iterates through, you'll see you have a whole lot of nulls going on there, even though that node is in the middle of the list for the other order somewhere. Some of you also had some bugs in the addition step, so the data is getting lost in the shuffle. So what you want to do is draw out the list, right? You don't need to draw out both the names and the weights. You can visualize those separately, right? Low 1 points to the 100 weight, right? When you want to create in a 200 weight person, it should link up like this, right? And when you're testing your data, it's best to try to do insertions so that it goes into various places in the list, right? So we have 100, 150, 200, lots of different places we can add at the beginning, the end, and there's a couple of middle places here. So when I'm testing your code, I'm throwing data that's going to want to wedge its way in all these different places. Yeah, if you're maintaining 2 separate lists, it's not going to take 30 nodes of space, which is not what we want. We want list and 2 ordered lists. Like what we were talking about. Excuse me 1 second. Cold medicine only does so much. Okay. We're talking about last week the databases and what B trees are used on databases. So when you have a database table, say we have 1 million employees at our company, and we have an employee database. And so the employee name, first name, last name, address, number, password, whatever we're storing. In the database, we just have the 1 copy. All right, Bob Smith, employee 1, password, password. If I want to print out my employee database, I don't want to go in and sort my first name and then print it out and then go to my database, sort my database by last name and print out. That is going to be expensive operation. So what we do is maintain an ordered list on top of the data. That's what we could do is by creating indexes on top of the data. So that's what we're doing here with our doubly ordered list as well, where the pointers are just maintaining the order. So if I want to go back and forth, print by name, print by weight, I can go back and forth, print by weight, print by name. It's just going to iterate one time across the list and be good to go without wasting a bunch of space. All right. This kind of makes sense. A fair number of you have got it cleared. And you're good, but everyone else, if you lost points, you're gonna need to fix that if you want to get some of those points back. If you haven't submitted, hopefully this helps you unblock. Yeah, we're about to start exam 2 after we take a 5-minute break. Another thing to point out, waiting to the last minute to turn in your program assignment means you have no opportunity to get back all the points you lost if you do something wrong. So everyone who turned in before yesterday had a graded cycle before that, and if you lost points, you could have gotten all your points back. People who turned in after 8:30 p.m., I'd already finished grading for the day, so you didn't get into a grading cycle until today, which means now you're past the due date, so you can't get all the points back if you lost anything. Draw what 2 lists look like. Well, lists, if we have, where's my, there. Right, if we have 5 people, let's do 4 people. 4 people fits better. Let's see. That's gonna work. All right. Abe, Doug, Carla, and Steve. Okay. So initially, Abe, being our first data point, comes along. It's the lowest name and it's the lowest weight. Doug comes along. He's after Abe, but he's going to be before. He's after Abe in name order, but he's going to be before Abe in weight order. So what happens is our other pointer, these get updated. So this being our smallest person. Carla's going to come along. She's going to point to Doug. And instead of Abe pointing to Doug, oh, that's a bit more than I wanted to delete. There we go. Abe points to Carla. And instead of Doug being the lightest person, Carla is now the lightest person. So if I were to print by weight, goes to Carla. 150 points to 200, 200 points to 250, and we print out Carla, Doug, Abe. I want to print by name. Goes to Abe, Abe's 250, Doug's 200, excuse me, Abe's 250, Carla is 150 and Doug is 200 by following that set of pointers. All right, and Steve comes in. So Steve's bigger than Abe, bigger than Carla, bigger than Doug. So Doug point to Steve. 175 is bigger than 150. So it goes in between here. So we'll have to, oh my, oh boy. It's poor Doug. It's casualties of war. I'll have to put him back in there. Doug. I guess his box was just too big. All right. All right. So the 150 goes to 175. 175 goes to 200. Okay. Let's go ahead and take 5 minutes. And the last thing we'll do for tonight will be go over test 2. So go and unmute. Okay. Test 2. All right, so we've got our reverse Polish. So we've got our stack building up 7-6. After our first addition, we got 13. Then 5 and 4. Balance stack was both 13 after subtraction, so we can do our subtraction. 5, 4, 4 from 5 is 1. Top of stack is the 1. Push 3 and 2. Multiply gives us a 6. So we have our 6 over here. And then the final answer, so we'll get addition gives us a 7. Push 1. Add those and then subtract for a 5. Questions on number 1 before I erase all that fun annotations? All right. Close drawings. Long, fine, recursion. No, not every function is recursive. Function has called itself in its body. It's recursive, can be recursive. Function can be recursive even if there isn't a call. If it calls back to the first, yes. Base case stop recursion. And this is the exact opposite. A recursive function that could be written as a loop should be written as a loop, not as recursion. And Stack Overflow, if we have a bad base case, or a bad or poorly written base case means we don't actually get to the end, so we overflow the stack. Pivot selection. So the first one could be our pivot. Middle one could be our pivot. So we have 7 values here. So 34 is our middle one. And we have a median of 3. So 19, 34, and 41. 34 is the median. So 19, 34. Selection sort. So we've got 8 is good. And we got 11 next. 11 and 42. We'll swap. Merge sort. All right, so we're going to divide this up. First 2, that's already good. Next 2, that's already good. And then this first 4 will be merged. And that's already merged. So this first 4 are already in good position. So the first 2 of our right set, that's already good. And then we have our first 2 from the next part. Those are not in order. So 41 and 59. 41 and 59 need to swap. 41, 59. Merge sorts n log n, quick sorts n squared, n squared. Everyone's n squared except for merge sort. Where's the bugs? All right, return type function or return type of function is int, takes an int. That's good function header, curly braces, whatever. If p equals 0, spit out 0. All right, so if it's 0, we spit out 0. Otherwise, we're going to print the result of our function call. It returns back an int, so that's good. And we can divide p divided by 2. So our base case is getting to 0. So 10 divided by 2 is 5. 5 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 is 0. So this will work as written. So there are no bugs. We put 0. Which of these is a recursive call? So that's line 6. Which one swaps the most in the worst case? That's bubble sort. Right. Merge sort doesn't swap. Insertion sort doesn't swap, so you eliminate those two. Okay, memory addresses. What we have here, 1400, 12 rows, 9 columns, and we want 5, 6. So we got 5 times 9 plus 6 times 4 per plus our 1400. Should be a 1604. My math was working. 11, 0. All right, so 11 rows, each of which are 9 wide. 4 bytes per plus our base address. 1796. And we can double check our numbers in a second here. 08, that's just plus 32, so 14. 32, and first address, same as the base address. All right, so to bound our range, 1400 is our minimum memory address. Maximum memory address, 12. Rows, 9 column. Oh, okay, can't use the keyboard. 12 rows of 9 columns, right? There are 108 elements in the matrix. 4 bytes per element means there's 432 bytes of allocation. So get back here into my text. 1828 would be the last possible valid memory address. So another way to double check our work, make sure things are lining up. All of our answers should be somewhere within that range to be good. Which sort is this, right? So we grab an element into a temporary, start one before that, make sure we don't go off the beginning of the array, and compare the two and shrink down. Shifting values as needed, and then dropping it back in there, right? So that's going to be our insertion sort. Yeah, using insertion, find the first one's an incorrect state. So we have our initial state, 2 shifts over, and then 1 all of a sudden moves. So row 3 is incorrect, right? Should have had just 259 as row 3, and then 1, 2, 3, 5, 9, all fun stuff. Anyways. All right, pivots 28. So 17 is good. 45 is out of place, so that will swap. 24 is not good, so that will swap. All right, so 24. Oops. 24 is over here now. 45 is over here now. So we go in back to this side, we find 51 is out of place. Jump to 88, that's good. Jump to 14, that's not good. 14's out of place. So those will swap, 14, 51. Then we get to 35. 35 is going to be our divide line. All right. So we can go ahead and stop right there because we'll, let's see, we're going to swap 35 first. Let's see. This side gets over to here, and then 35 is happy. This side gets over to here. So now we're good. 35 will stay there. 28 ultimately gets here with 14 over on that side. So give it a quick sort. And lastly, some code. What are we doing here? Add to head. All right, so link star n equals link. Seems a little small. And info equals data. And previous 0 and next 0 as our default starting point if the head is equal to 0. Then the head equals tail equals n. Otherwise, just add to the head. So n next equals our existing head. And previous, since this is the head, it's still going to stay 0, so we don't have to worry about that. And then the head equals n, and that should be good. Let's see. Now we need to do a previous. Do we need a previous? No, because we're adding in front of the head. Head next. No, we need to do a previous. Where's my previous? And let's see here. Oh, I need to do a drawing because I'm starting to lose my brain. We have a node. It's 15. It points nowhere. And I want to create my new node. So this is head. All right, now I think my brain's working. So head previous equals n. All right, there we go. And previous equals n, so that'll link that to there. And next equals the head. There's our n, and whatever our data point is, that goes nowhere. And then this becomes our head. And there's the test. See if I goofed up the key at all. No, it looks like the key is correct. 42. Should have remembered to turn that off so you can see your answers. You can see your answers now. See what didn't quite line up with what we were expecting the answer to be. Print 0 twice. Print 0 twice. Let's see. I can see an argument for that because it prints 0 twice. It prints 0 twice because the base case is printing 0 and it then returns 0, which turns around and prints 0 again. Yeah, you can go ahead and message me that in Canvas. I can take a look at your test answer. Because one can say it's a little bit redundant to print the value out twice. It'd be a little bit tricky to try to write a function that's doing what it's doing such that it doesn't do that, since it needs to return data back. But it's a fine argument. You just get rid of the print. So actually not a big change. Isn't 41 a pivot? If 41 either has to be the middle value or a median to become a pivot. The last value in the array is not going to be a pivot unless it's a median value. So if its value were like 27 or something like that, then we could use it as a pivot because it would have been the median. It's the only way that the last value can be used as a pivot if it's smaller than one of the other two values that we're choosing as the median of 3. Exactly. So the median is 34, which means 41 would not be a pivot. Right? Because 41 is an extreme value. We want the pivot to be not extreme, which is why we take the first, last, and middle element and throw away the 2 extreme values and use the moderate value amongst them, because that works as a better pivot to split the ranges in half. It asks for which 3 could be a pivot. Or did I confuse myself? Where are we? Where is, I guess that's number 2 or something like that, isn't it? Number 3, using each of 3 methods, which of the values could be used as the pivot? Right, so 41, 34, and 19 would be considered to be the pivot in the median of 3. But when we're with those 3 values, 34 is selected. Now you can assume 0 values for the number 21. Typically, we have a default constructor that does mem set everything to 0. No, median, you sort the values and you take the middle value, right? So here, median. Where we got math world. Math is fun. There we go. Right, so you sort all the values and the number in the middle, and if there's 2 numbers, then it's the average of those 2 numbers, which is why I chose the length of that array to not be even, so I don't have to have floating point numbers as options in that. All right, so find the middle of these 3 values, sort, and then the median. The only time there's a division is if the range has 2 numbers in the middle. And you have to average the 2 together. Yep, lowest test score is dropped and it's already being dropped. So your grade is already reflecting dropping this test or the previous test. Because it asks for all 3. Right, all 3 methods. So we have 3 methods of choosing the pivot. The first method is to just use the first value, right? The laziest approach, you use the first value as the pivot. The next laziest approach is to use the middle value as the pivot. And then the third approach is the median of 3, which takes 3 values, sorts them 19, 34, 41. So these are already sorted, and then takes the median. The median of 3 is always choosing 3 values, yes. Right, so we'll do, even if this is an even length array, integer math will push just over to the 1 and choose from those 3 values. Right, so even if we had 7th over here with 54, let's say, okay, let's make it 25. All right, so say we have 7. Get my eraser. All right, so let's make this array bigger. Now it's asking the same question again. First value, middle value, last value. that's the pivot. Because we go 19, 25, 34, and 25 is the median. Right, because like cout, which is a function, doesn't call itself. Or push, which is a function, doesn't call itself. The vast majority of functions that are or ever will be do not call themselves. Right, recursion is a subset of functions. You'll find them often when you have nonlinear problems. Other questions for the practice test? Yeah, there could be 3 values, just like this one here. If we added 25 to the set of data, right? So it's completely driven based off the data. There's gonna, for this question format, there's always at least 2 answers, because the first and the middle are always gonna be selected unless the values happen to be the same. There's always at least 2 positions that are going to be the answer to this question. And sometimes this third value could be the answer. Just depends on its value, right? So if it was 1, or if we come here and add 7, and its value is 10, whatever. When we do the median of 3, we grab 10, 19, 34, and 19 is a pivot. So we're back to 19 and 34, the only pivots that could have been, that can be selected on this array. All right, so the answer to the question isn't the first, middle, and the last. It's first, middle, and median of the first, middle, and the last. Okay, if we don't have any other questions, or isn't the question? Let's see. Merge sort. All right, let's go hit the merge sort. But that'll be all for today after we finish answering questions for the test. So let's see, merge sort. So our merge sort. All right, so we divided the array in half. And we divided the array in half. And then we divided the array into these 2. Right, which we divided in half. Then get to these 2 one-digit lists, 1981. That's merged, and then we get to this point. So these 2 are not yet merged. So they need to change state next. And then there would be one more state after this with 17, 19, etc. 29, 38, 41, 42, 49, and 81. Right, so this one wasn't asking what's wrong, it was asking what's next. What's the next state change? And these 2 numbers would be moved in the next state change. Right, so if I were to ask this question again, and they are already in this state, right? The first 4 are sorted and the last 4 are sorted. The next state change would be merging those two lists together. So it would have been most everyone, yeah, everyone but 17 would have had a state change. It doesn't matter for, right? So right here, this is an even length list, 0 through 7. The middle position is here, right? So let's clear all this. So if we're quick sorting this, right? First, middle, last. Take the last index divided by 2, and that is 3. And that tells you where the middle value is. Yeah, Mark just messaged me in Canvas about that empty space. Quick sort question towards the bottom. Yes, the pivot one. Yeah, so we're talking about earlier. Candidate value. Oh, this is the swapping one, right? So 20 is the pivot. So we start on the left-hand side, look at 17 and we say, we're good. Find 45, say that's not good. Let's jump to the right side, 24, not good. So swap. Jump back to left-hand side, 51, not good. 88 is good, stays there. 14, not good. So those two will swap. Jump back to the left-hand side, we don't like it. Jump to the right-hand side, says 35 is good. And it gets over here and we get the crossover. That causes the pivot to swap over here with where 14 is. 14 goes to the front. And we now have 28 sorted. 14, 17, 24 on the left-hand side, smaller than the pivot, 28, 35, 57, 88, and 45, all greater than the pivot. Greater than 28 over here, and less than 28 over here. And to make that happen, 24, 14, 57, and 45. Right? They had to shuffle around. Yeah, those are the values that were found in the wrong partition. Or in other words, they had to be swapped. Yeah, values are on the wrong. Yeah, that's terrible. Underlining, wrong partition. Those are the ones that get swapped. Yeah, I don't say which values are swapped because then people start getting confused about the pivot because the pivots then get swapped as well. So they might not include those two values. So by being explicit, just saying which values are wrong partition just limits it to that set of data. Yes, please ask anything is confusing on the test, ask in the chat window because English into computer science is a significant translation there where things can go different directions very, very quickly. And you can have a single sentence in a requirement document that turns into weeks of work. Any other questions? Because 88 is greater than the pivot. So it belongs in the right partition. Right? Values that go in the left partition are values less than the pivot. Values that go in the right partition are values greater than the pivot. So if it's already in the right partition, if it's already in the correct partition, it's in the right partition. It's where it should be. Okay. Well, because that's the left side. Or what? Right, so I'll do it again one more time. Right, so there's our pivot. Left side, right side. Left side goes over, finds someone that's wrong. Right side, immediately finds someone that's wrong. So those will swap. Left side continues growing. Finds someone that's wrong. Right side goes down until it finds someone that's wrong. And we find 14 who's wrong. So they do that swap. Left side gets here, so we're at 14. Left side grows. Right here. Right, and it thinks it's found someone that's wrong. Right side needs the other half of the equation. Right side's happy with it. And the right side gets to here. It sees that we've crossed over. So we've stopped. This does not move. And we found our divide point for our partition to swap in, our pivot to swap into. Right, so 51 is an answer because it is on the left side when it should be on the right side. All right. We'll see you next time.
Thank you, Professor.